So hello everyone. Today we have Zhengdi Sun to tell us about self-duality and gauging non-invertible symmetries. Please take
Uh, okay, thanks for inviting me to speak here. And today I want to tell you something about the self-duality under gauging non-invertible symmetries in 2D CFT. This is based on the work I did with Yichu, and I'll try and think Yichu is in the audience. Okay, so to get started, I want to give a very brief introduction to generalized scalable symmetries. Like one of the recent themes in study QFT is to study the so-called generalized scalable symmetries. In this picture, the conventional zero-form scalable symmetry are represented as codimensional one topological surface operator, a U of G, labeled by group elements G in some group G, and diffusion of the topological defects are governed by the group multiplication law. In this talk, we kind of interested in doing this generalization where diffusion of the topological defects are no longer governed by the group multiplication law. Therefore, the topological defects generally do not admit a inverse, and that's why people sometimes also call those non-invertible symmetries. And given this new concept, it's natural to ask, okay, can we systematically find those non-invertible symmetries? Like starting from 2021, there has been rapid developments in this field. Like people come up all sorts of ways to finding these new non-invertible symmetries in 2 dimension, also in like higher dimensions. Here are some reference. Certainly, there's a long list of references which I do not include, and I think Sakura has a good lecture notes on this, which contains up-to-date reference. And also, the other questions one can ask is, what can those non-invertible symmetries tell us? Well, it's just like the conventional symmetries. It can impose selection rule on amplitudes, constrain the infrared phases, and things like that. So in this talk, we kind of want to provide an interesting answer to the first question. The idea is given the theory T with a so let's start from an old idea, which says given a theory T with anomaly free finite invertible symmetry G, and gauging this symmetry G would generally lead to a new theory, which we call T mod G. But then gauging this G on half space would generally lead to a topological interface between these two different theories. But if it happens that the T is self-dual under gauging this finite symmetry G, meaning the T is the same theory as the T gauge G, then the topological interface become a topological defect in the theory T. And this defect is generically non-invertible. Now, this construction is well known for many years in 2D CFT. The fusion category was worked out in a famous paper by Tambara Yamagami back in the 90s. And this thing is appears in I think CFT and has been worked out in some other CFTs. And recently, this construction has been generalized to higher dimensions. So in this talk, we want to generalize this kind of well-known old ideas along a different direction. Namely, we want to consider 2D CFT with gaugeable non-invertible symmetry. In this particular case, we are interested in this rep H8 and try to see if we construct any theory which are self-dual, or find any theory which are self-dual under gauging this non-invertible symmetry, and try to explore the corresponding duality defects. Okay, so here is outline my talk. So I will start with a brief review about the topological defect and their gauging in 2D CFTs. I will do a quick review on how to gauge non-invertible symmetries in 2D CFTs. And then we will focus on how to gauge in the rep-H non-invertible symmetries and present a few examples which are actually self-dual under gauging this symmetry. And the second part of the talk would focus on how this self-duality would lead to non-invertible symmetry defects, and we will provide some more details on the study of this duality defects of gauging rep-H non-invertible symmetries.
So can I ask if this is the simplest example of non-invertible symmetry where a self-duality can occur? So what I have in mind is rep S3. There already, I think there is a way to gauge rep S3 to get rep S3. There is a Z20 form symmetry in the sim TFT.
Oh, right. I think you could do that. So the thing we are considering here is we want to gauge the full category using the algebraic object whose quantum dimension is equal to the quantum dimension of the rapid shape, like of the fusion category. So in that sense,
I see.
I mean, I think if you give the entire rep S3, you will get S3, right? So
So here there's a unique self-duality defect you want.
yeah, in the Z2 extension.
I see.
Yeah.
The rep S3 will violate that.
Yeah.
Thanks.
Okay. Thanks for the questions. All right, I will continue. Oh, yeah.
Sorry, I just want, it's a related question to Lakshya. So you mean if I take any rep G where G is a group, then I gauge the entire rep G, then I wouldn't get rep G back, right? I would get G back. So is rep HA special because H8 is not a group but half algebra?
I think that's probably true.
Okay.
I don't really know example like if you gauge the entire group, you should get the group back, I think.
Right.
Yeah.
Okay. Thank you.
Yeah. By the way, it's a good thing to point it out that like the HA here is a Hoof algebra, it's not a conventional group. Yeah, thanks.
Right.
Okay. So let's I want to start with the first part of the talks, which I will quickly review the topological defect line and comments on how do we gauge it in 2D CFT. Well, so first, let's talk about topological defect lines in 2D CFT. Well, the zero-form symmetries are described by a topological line operator LAs. We focus on the set of topological defect line which forms the fusion category. In particular, this means they are finitely generated, and we can find a finite number of simple lines, which we denote LLAs. Now, what you can do with this topological lines, you can do a global fusion, namely you try to put the lines on top of each other, and then in general, they would give you some non-simple lines. You can expand in terms of simple lines. And then you would find this fusion coefficient, which generally integers, positive integers, well, non-negative integers. And then what you can also do in 2D is to consider local fusion, where you kind of fuse those defects together locally. And then the junction is actually the space of all possible junction forms a vector space, and the dimension is exactly given by the fusion coefficients. And we will pick a basis and use this Greek letter little mu going from 1 to the dimension of the vector space to denote the basis we pick. I also want to point out this because of slightly abuse of notation. Later on, we will use mu as the junction for the algebraic objects, and it should be obvious, like don't mix the two. Well, okay, so what happens is there are some additional data called the F symbols one need to specify, namely when one try to fuse 3 topological defect lines together into the fourth one, there are generically 2 different ways of fusing them, and this way of fusion, like 3 lines, are kind of also described by vector space, but you can kind of pick a basis to either expand it in this and in that. And generally, they are related by a linear transformation whose coefficients, what we call the F symbols. So in general, a feature for the fusion categories, you can have the category or those topological defect line has the same rule, but yet because they have different F symbols, you should treat them as different fusion category or different symmetries. And those would generally lead to, they are kind of physically distinct as well, because if you look at the spin selection rules of those defect Hilbert space corresponding to lines, they are actually physically distinct. Okay, so let me give you a few examples. For example, you can think about finite symmetries, describe some Is there a question? Okay. The simple lines are labeled by group elements G in a finite group G, and the fusion rule of the simple lines are governed by the group multiplication law. And then the F symbol was kind of given by the omega, which is I think it's boundary in well, in the third group cohomology encoded to Hooft anomaly. Now, this means really two ways of resolving four-way junctions are differed by a non-trivial phase when omega is cohomologically non-trivial. So you can't. So when omega is cohomologically non-trivial, you can't really get away, shifting away this thing by a redefinition of your junctions. As well, we'll see this would be an obstruction to gauge the symmetry. Another example I want to mention, which is we will actually use later, is the Tambara-Yamagami fusion category, which is TYA, chi, and epsilon. So to tell you the categories and tell you the simple lines, which given by a finite group A, where A is abelian group together with a non-invertible line N. Sometimes this is called the duality line. So this Tambara-Yamagami really means if the existence of this fusion category would mean the theory is invertible under, or it's self-dual under gauging this finite group A, abelian finite group A symmetry. And the fusion rule, for the A part, it satisfies the group multiplication of the finite abelian group, and the fusion rule of A with a duality line was given by this. So this additional data, chi and epsilon, determine the F symbol. So chi is a choice of symmetric non-degenerate bicharacters of A. That means first it's symmetric, second it's a character, it's a bicharacter, and also non-degenerate, meaning if you for any A1 in A, if you compute chi A1, A2 equals to 1, that would imply A2 is it's an identity element. And epsilon equal to plus minus 1 here is a choice of the plus minus sign known as the FS indicator. Namely, it's a phase of this particular F symbols. The full list of non-trivial F symbol was given summarizing these slides. And indeed, you see the epsilon is a phase of this, this F symbol when you take, well, if you take AB to be 1 and 1, here it's become 1. So the epsilon was indeed the phase of this F symbol. Okay. So some. Okay. So the Eisen fusion category. So I will mention two fusion category which I'm interesting or we will use in the talk. The first one is the famous Eisen fusion category. It's described as self-duality under gauging the two symmetries. In this case, when the group is Z2, there's a unique non-degenerate symmetric bicharacter, which is the non-trivial elements is chi Z2. If you evaluate on the non-trivial group element eta and comma eta, it gives you -1. And the Eisen fusion category are the ones with the FS indicator equal to plus sign. The second thing, like fusion category interesting is the rep H8. Here I should mention like H8 is really a Hooft algebra. It's not a conventional group. It's some Tambara-Yamagami. It's the same as the Tambara-Yamagami with A equals Z2 times Z2 with a diagonal character, which is if you parameterize Z2 times Z2 in this way, this character is given by this. And we choose the FS indicator equal to plus sign. And I want to mention that if you're stacking two copies of Eisen and fusion category, then it contains the rep H8 as a fusion subcategory. And in particular, the duality line in the rep H8 is related as the product of the two Eisen duality line. Okay, that's for the fusion category part. And okay, I need to also review this. So given a topological defects, we can place a 2D CFT on a cylinder and insert a topological defect line along the time direction. And then under state operator correspondence, so first, if we quantize this theory on its S1 with the defect along the time direction, then we will generally get the different Hilbert space. We will call it the defect Hilbert space, labeled by the line L. And then on the state operator correspondence mapping of the 2D CFT, it will map to some non-local operator O with a topological defect line L ending on the O's. And the action of the topological defect line is described by this lasso action. So pretty much like the L2, it's a symmetry operator, and you want to measure its action on a non-local operator O ending on the line L1. And in general, if your fusion category is complicated enough, just specify L2 and L1 is not uniquely determine what you mean by the symmetry operator. You also need like the L3 and the when some junctions mu and nu to fully specify like the symmetry operator. So an important class of the observables we can compute with the topological defect, the twisted torus partition function, which is this one. So indeed, so first this partition function is a trace over the defect Hilbert space of L1. So we take the time direction to be along, to going up. And then, so this partition function computes the trace over defect Hilbert space L1, and it measures the operator L2, which is specified by this additional line L3 and mu comma mu. In the case of invertible symmetry, like this thing is really uniquely determined. You only need to specify L1 and L2. Okay, so now we're ready to move on to the next part. I want to first give an example of gauging invertible symmetries and then motivate it why we can use the algebraic object to gauge non-invertible symmetries. And so let's get started. So first, as a simple example, let's consider a 2D CFT with anomaly-free Z2 symmetry generated by some line eta. Then the symmetry operator is a topological defect line, as we said. So the topological sector of the theory T is given by, so you can look at the Hilbert space H, and we'll organize into irreducible representation of the Z2 symmetry. So it contains the E2 even part and the Z2 odd part. And we can also look at the defect Hilbert space, which is H eta. And because in this particular case, Z2 is free of anomaly, it's also organized into the Z2 even part and Z2 odd part. To the torus partition function of the theory T gauge Z2 is computed as this one. So if we try to interpret this Z2, like this partition function, so the first two terms says we are projecting onto the Z2 even sector of the Hilbert space of HT. And the second part saying we are keeping the E2 even space of the Z2 twisted sector, which really the defect in modern language, the kind of the defect Hilbert space of Z2. So the topological sector of the T gauge Z2 is given by this, and in particular, I want to emphasize, as I said, it leads to reorganize of the spectrum, and the Hilbert space of the theory with Z2 gauge is really contain two parts. One is the H plus, and so you take the Z2 even from the Hilbert space and take the Z2 even states from the twisted sector, and they become the Hilbert space of the T gauge Z2 theory, and then and furthermore, because you gauge the Z2, there will be a quantum Z2 symmetry. So the Z2 even state from the twisted sector will be charged non-trivially under the quantum Z2 symmetry, which I denoted as the Z2 hat. All right, so to generalize to non-invertible symmetry, it is convenient to freeze the gauging process in terms of algebraic object. In this particular example, to rewrite it, we can introduce a group algebra of the Z2 symmetry, which and together with a fusion and splitting junction, which in this form. And in particular, if you so then the gauging was really look like inserting a mesh of this Z2 algebraic objects on the torus, and indeed, if you expand, you would find the Z2 partition function we used before. So this is kind of what you would use to generalize to non-invertible symmetries. So the The ideas is, so given a generic, Riemann surface, we can consider triangulate the Riemann surface. And then given a fixed triangulation, they will want to insert a mesh of algebraic objects along the edge of the relation. So we will have some diagram like this. But then in order for this process to make sense, it must be invariant under triangulation of the Riemann surface. And so any triangulation of the Riemann surface can relate to each other via a sequence of this fusion move and the bubble moves. So that means we only need to impose a constraint that the mesh is kind of invariant under these two basic changing of triangulations. So if we put different orientation of the algebra on this, we will get different of constraints about the fusion splitting junctions. Mathematically, those conditions are summarized as kind of a symmetric delta separable Frobenius algebraic object in the fusion category C. Like it's need to satisfy a bunch of constraints, for instance, like this, and there are many additional more. But the good thing is every simple haploid algebraic object, haploid, I think really means there's a unique identity here. It kind of admits a unique co-algebra structure, namely the splitting junctions, and well, some technical detail, such that it become a symmetric delta separable Frobenius algebra. So what that says in practice is once you find some algebraic object together with a fusion junction that satisfies this first constraint, then it's automatically imply you can find a unique splitting junction mu check. I think we call it mu check that make it a good gaugeable algebra. You can summarize them. You can put a mesh on the torus and compute this torus partition function basically. So in terms of actual calculation, this is basically three conditions what you need to find mu and like mu check. So to give you an example, like familiar example, we can consider finite group G. And in this case, gauging the group G, we will choose its group algebra. And we expect the junction with some unknown coefficients, and we try to solve it. So the constraint says this diagram must be the same as this one. So to solve it, you kind of expand these two in terms of simple objects. And this diagram and this diagram are relayed by F move. So generically, there will be a F symbol, which is omega. So I realize that this is really says in terms of group homology, says d psi equal to omega. So it won't have a solution unless omega is cohomologically trivial, which really says, okay, omega, when it's cohomological non-trivial, it's the total anomaly obstruct the gauging of the finite symmetry. And when omega is indeed trivial, the solution, the inequivalent solution is parameterized by the H2 group cohomology class. And the splitting junction can be determined from the constraint, which the other two constraints mentioning, and which is equal to the one inverse, which is like 1 over psi g comma h. And if you organize it on the torus, you find you realize this as a discrete torsion that you get when one gauge the finite G symmetries. Okay, so now we are ready to talk about the rep H8. So first, what we do exactly as we did in the invertible symmetry case, we find the algebraic object, and because in our paper or in this talk, we are kind of always interested in the special type of algebraic object where the multiplicity of the simple line L is given by its quantum dimension. So in that sense, this is kind of the largest possible algebra you can write, simple. And then the number of inequivalent object of this particular form is the same as the number of the fiber functor. I want to mention, like, as people has asking before, like there are other algebras of the rep H8 with small quantum dimension, which are also gaugeable. For instance, you can construct this 1 plus AB plus N. And there's some more discussion on this in some like two paper which come slightly later after our paper. So if you're interested in this case as well, you can think about, you can take a look at these two papers. Okay, so similarly, we expand the fusion junction in terms of simple objects and try to solve the constraints, and here's what we find. And the splitting junction mu check can be determined using these two conditions. So I won't go into the details, but just as a case of invertible symmetry case, the torus partition function for gauging rep H8 can be computed by expanding these diagrams, and you would find a very complicated expression like this. So I want to pause here to explain what's the interpretation of the partition function of this, this gauging process. So in the Z2 case, we know that gauging Z2 symmetry, you kind of keep the Z2 even state from the Hilbert space and also the Z2 even states from the twist sector. Can we find a similar understanding of this gauging process? The answer is yes. So in this case, the defect Hilbert space is much more complicated because this fusion category has 5 lines. 4 forms the Z2 times Z2 invertible symmetry, and there's also a duality line. So you have to consider 5 defect Hilbert space. So they're generally speaking 3 classes. So the first one is the Hilbert space, which you can also think about the defect Hilbert space as an identity line. And there's also defect Hilbert space of the AB's Z2 sum, so the gauging would project. So here is the action of the topological defect line on this Hilbert space, and these are the possible representations. So as you can see, gauging rep H8 would project down to the this particular sector and this particular sector. I want to mention here is project onto the -1 and -1 sector of the ZA times A and B is because you have a non-trivial discrete torsion for the corresponding Z2 times Z2 part. And similarly, for the defect Hilbert space HA and HB, you would project down to these particular sectors. But it's kind of interesting here, if you look at the partition function, there's a undesired factor of 1/2. It's actually not a problem because, as I said, the existence of rep H8 implies the theory is self-dual on the gauging Z2 times Z2. So from really what happens is this sector is identical at this sector. So they are kind of like the same sector. So what this says, you're just keeping one copy of the sector, like the same sector. So the 1/2 is not a problem. And finally, let's look at the defect Hilbert space of the duality lines. And then if you look at the form its projectors, it will project down to these particular sectors. Now here, I'll give a quick comment that because, so in order to fully specify the, Nadi, do you have a question?
Yeah, what happened if you did it in steps? So imagine you just did standard gauging for a Z2 subgroup. Then what will you do? What will you have to do later?
Oh, you mean sequential gauging, something like that?
I don't know what sequential gauging means.
You mean what? First.
So I just took this thing and I just gauged a Z2 subgroup and I get something else. And now what do I need to do now to achieve what you have just done?
Yeah, I'm not sure on top of my head, but I think it's a doable process because you need to get some other symmetries that you get to accomplish this step, I think. Well, yeah, I don't know on top of my head, but I think you should be able to gauge some other symmetries in the theory you get after gauging the two to get this particular theory.
Because normally when you gauge a symmetry, you can first gauge the subgroup and then you can try and gauge the rest.
Right. Yes. Yes.
Okay. Thank you.
Yeah, thanks. Okay, all right. So, okay, so on common side in terms of the actual calculation, one can use the fact that the theory T is self-dual under gauging Z2 times Z2 to simplify the expression. So the punchline is once you take this into account, the torus partition function can be computed once the action of a rep H8 on the Hilbert space H is known. And then you can use this starting with this twisted partition function and their modular transformation and combine them together, and then one can get the you can compute the torus partition function. Yeah. So let's consider a few examples. For instance, first we can consider sequence compact boson on the orbifold branch. So at the generic, so the point is the rep H well, as I pointed before, like in order to compute the torus partition function, of gauging rep H, you only need to know the rep H8 action on the Hilbert space or equivalent on the primary operator, and indeed this is known. So roughly the idea you can kind of sort of deriving it is to start with the circle branch, and there's a Z2C symmetry. And if you gauge the symmetries, you would go to the orbifold branch, and then from there you can kind of work out all the symmetry actions on the primaries, and which is being worked out in the paper by Ryan and Ifan. And then if you do the calculation, you would find this gauging rep H8 symmetry would actually map you from orbifold branch to the orbifold branch, but they kind of flip the radius, taking R to 2 over R. And in particular, this means the R orbifold equal to square root of 2 is a fixed point of this operation. And indeed, if you look at this point, this is like 2 copies of the Ising theory. So what we find is 2 copies of Ising CFT is actually self-dual on the gauging rep H8. That's one example. Now, motivated by this example and also the thing I mentioned before is if you take 2 copies of Ising fusion category, then it is actually contained in rep H8 as a subfusion category. And the question is, if we take any 2 theory with Ising fusion category symmetries and take 2 copies and stack them together and try to gauge the rep H8 subfusion category, do we find self-duality? The answer is generally no. So the way to see that is to use the symmetry TFT of the Ising symmetry to organize the partition function of the topological sectors. And because kind of like the S and T matrices for the bulk symmetry TFT is known, you can kind of use that to capture how those topological sector will transform onto the modular transformation, and then you can compute the partition function. So this is the partition function you get by stacking 2 copies of theory together, and this is the one you get after you gauge rep H8 symmetry. So generically speaking, those 2 theories will not be identical. So in particular, that's pretty much says it's generally very hard to find the theory which are self-dual on the rep H8. You basically pick up 2 generic examples, you won't find self-dualities. And here we provide some examples. But it also kind of provides a way to see how do you find self-dualities. The idea is, if you notice that this special case where this partition function would factorize of a particular topological sector would factorize a product, and then you would find the self-dualities. So using this, we can find a pair of examples, well, which satisfy this is actually the Ising CFT and the monster CFT, because in Ising, we know the characters kind of factorize because just have not any characters. And the monster kind of has the same property. So if you try to stack these 2 theories together, then they would just automatically satisfy the self-duality condition. So in other words, we've kind of find 3 examples. You stack Ising CFT with Ising CFT. So that's one example we already find. And then you can stack Ising with monster or 2 copies of monster. They will all be self-dual on the gauging rep H8. So this is a set of examples we find. Okay, so now we are ready to move to the second part of the talk, which is the self-dualities and the non-invertible symmetries. So the idea is once we realize some, theory is self-dual under gauging some non-invertible symmetries, it is then possible to do a half gauging to generate a symmetry defects, and in general will be non-invertible. So for a generic theory T with some fusion category C symmetries, if you gauge the C, well, assuming C is gaugeable, and then you would get a different theory with different symmetry. And in general, the interface is a simple object in this particular category, which the category is of A module, yeah, left A modules, maybe right A modules. But if we are interested in the algebraic object, which in this particular form, then there will be a unique object in C of A. This kind of also relate to the comments like people or questions people have before. If you take algebra to be of this form, then the interface, the category of interface will contain this unique simple objects. And in the special case where where the theory is kind of identical after gauging, it will give a unique like a duality each defects. Okay, so here I was just saying the special case of the theory and the symmetry are kind of identical after the gauging. Then you can kind of the interface kind of become a duality defect and can determine the fusion rule of this duality defect with the lines in the lines in original category. And pretty much because a line is gauged. So if you try to move the line across the defect, it must be transparent up to quantum dimension. So that really says L fused with D is the same as a quantum dimension times D. And from this condition, you can also determine this one. The other interpretation is because in this talk, we kind of restrict to the case that the duality defect is the same as its orientation reversal. So if you stack D with its orientation reversal and try to fuse together, then you will just recover a mesh of the algebraic object A because it's kind of sum over. But if you try to push it D and D inverse together, then we just find the algebra. Okay. So this fusion category together with this unique duality defects form a larger fusion category, which you can kind of view the Z2 extension of the original fusion category. Here we use an underline because we are interested in the case where this non-trivial Z2 greedy component contains a unique object D. So if you try to construct self-duality under gauging a smaller algebraic object in C, generally speaking, you will have more than one duality defect because there are some symmetry you are not gauged, and if you have a duality interface, you can fuse that symmetry which is not gauged with the duality defect to get a new one. So in other words, the duality defect is not unique. But here we are interested in the case where it is unique. So we use a underline in the east to denote this particular type of extension. So generally speaking, this fusion category is not unique, and this additional data would arise how we identify the symmetry C with a quantum symmetry in the gauge theory or the dual theory. So yeah. So let's consider an example. So for instance, the Tambara-Yamagami fusion category mentioned several times is indeed one of these examples. So in the new language, the original fusion category is just vector A, where A is an abelian group, finite abelian group, and the Z2 extension is just of this type is just a Tambara-Yamagami fusion category. And if you look at the fusion rule, it indeed satisfies what we want. And here the N actually plays a role of the D. And indeed, we need actual data, which is chi and epsilon to specify the fusion category. And the chi basically controls how you identify the original symmetry with the quantum symmetry. Okay, so for the H8, we can do a similar analysis. So we study this by solving F symbols explicitly, and we find the Pentagon equation, so we can solve F symbol directly, and we find 8 inequivalent solution to the Pentagon equations, and we denote the corresponding fusion category as something like this. So here I and kappa d and epsilon d are some plus minus signs, choice of plus minus signs in the F symbols. And in particular, epsilon d is a familiar Fs indicator for the duality line D.
Sorry, can I ask a question?
Yeah.
Maybe I missed it, but can you exclude in general the duality defect that you obtain procedure is not already in the category?
It's not alright. Well, I mean, it's just not in the category, right?
I mean, in this example, I see, but in general, because you explained this general procedure, essentially. But can it be in some case that you do this self-gauging and the new topological line was already part of the original category?
I thought that's unlikely because the duality line you absorb all the original lines. You don't have such a fusion in the original category.
I see.
I mean, if the line exists, then it would imply the theory is kind of self-dual. I mean, you can consider some kind of example. For instance, you can take isenfusion category and you say, okay, let's gauge C2 symmetry. And indeed, the theory is self-dual, which is also captured by the fact that the duality line is the end, right? So
yeah, I see. Because basically you're imposing that the algebra you're gauging is maximal in some sense. So I agree with Sean's comment. Okay. It would imply
I think
that.
go ahead.
Okay, thank you.
Yeah, I just want to say, like, in order to rule out this situation, is you want to see like gauging. So you have some fusion category, and you try to find some algebra, and like if you gauge it, if the theory is always self-dual on the gauging it, I guess the other would just say that this object is Morita equivalent to some trivial algebraic object. Unless these things happens, the duality line should not be included. You should always find some new lines. Okay. All right, so what we can learn from this fusion category, the first one is we'll give some constraint on the RG flow. The idea is because the quantum dimension of this D symmetry operator is 2 times square root of 2. It's not an integer, so that means the theory cannot flow to a trivial gap phase if you want to preserve the self-duality because of these quantum dimensions. This is a general result. The alternatively, you could try to write down an SPT for rep H8, which is self-dual under gauging rep H8. You're not going to find it. Okay. So finally, the thing I want to talk about is the spin selection rule.
Sorry, just out of curiosity, if you gauge the rep H8 of that fiber functor for rep H8, how many states do you get? It's not self-dual, but you end up with a gap phase described by some TQFT. How many states does that TQFT have?
Actually, I actually computed this, but I don't remember. Maybe
okay, it's okay. I can ask you.
Yeah. I think I actually computed at one point. Maybe Ichu remembers. I told him. Yeah. Anyway. All right. So the spin selection rules for the D defects. Okay. So here we will try to describe a physical implication which allows us to distinguish the 8 fusion categories we find. Namely, we want to cite the spin selection rule for defect equals HD of the duality defect D. So the point is, under the sequence of F move, I can show that the spin of the states in the defect Hilbert space of HD is related to the action of the following 8 operator on HD. So the first one is the invertible symmetry G acts on the defect Hilbert space. So because it's invertible, the junction is kind of unique, and this intermediate line is also unique to be D. So you really don't need to any other data specify it. The second type of operator is N. Now, because n fused with d is equal to 2d in this particular case, because the quantum dimension of n is 2. And so you, in principle, you would have junctions, non-trivial junction mu and nu here. So, so really, to fully specify the actions of the symmetry, you need additional things like a mu and nu, which both goes from 1 to 2. So they are kind of 4 operator of this type. Now, then you do this kind of rotation by 4 pi. At one point, so on one side, it will pick up the spin, which is e to the 4 pi s, but then you can use a bunch of sequence of f-mode to resolve this, and you'll find something like this. So in other words, this allows us to relate the spin to the action of the symmetry. Now, the F symbol also allows us to find the algebras that this U of G and U of N mu satisfied, and then we can work out all the E-reps satisfy the corresponding algebras and plug in here, and then we would get a spin selection rule, basically. So for example, if you take UG fused with UH, and after a sequence of 5 move, you find it's something like UG-H. So similarly, you can work out relation for the product of UG and UN, and UN and UG, and UN and UN, something like that. I think in the end, it's the commutative algebra, so you would only find the one-dimensional representations. But once you find that and you plug into this formula, you would find the all the allowed spin mod 1/2. It's mod 1/2 because here you have e to the 4 pi ISU, so you have to take square root. So really, it's only holds up to mod 1/2. And indeed, you see all these 8 fusion categories we find actually have distinct spin selection rules. That means they are physically distinct. Furthermore, these two I highlight with green are the two which appears in the Ising time Ising theory. In that case, you can do kind of like a bootstrap analysis, figure out the answer. It's actually some cosine like lines you get in the orbifold branch for the people who know this. And there are 2 copies it's realized because if you take Ising time Ising theory, there's actually a Z2 symmetry with exchange 2 copy of Ising, and then that Z2 fills that Z2 with the one type of duality line would get you from one to the other. So that's why 2 copies realized. So I think that's pretty much I want to say. So I guess it's 40 minutes approximately. So just thank you here and take some questions, I guess.
Yeah, thank you very much. Are there any questions?
Sorry, can I ask a question?
Yeah.
So in the standard Tambari Yamagami for a group like symmetry, you have the constraint that the symmetry that you are gauging must be abelian and non-anomalous. No, this is the standard classification.
Yeah.
And this is because you have to gauge the symmetry in order to get the self-duality, and also must be abelian because the quantum symmetry must be isomorphic to the symmetry itself.
Right.
Do you have some similar constraints here? Then the category must be gaugeable and maybe commutative. I don't know. Do you have some?
Yeah, here we kind of use, well, I didn't say this, but if you take rep-H8 and gauge rep-H8, the quantum fusion category is also rep-H8 in this particular case. In general, I guess you also have to require this, but I don't know a good way to actually systematically check this.
Okay.
Besides you work it out.
Okay, thank you.
I have a question.
Yeah.
So you said this this D topological line has non-trivial consequences on RG flows. What are the examples of RG flows preserving this D symmetry?
Actually, that's a good question.
I guess if you start with Ising square, there's no relevant information that can preserve this. I haven't thought about it carefully, but naive, I don't think there is.
Yeah, probably have to.
From the Ising square point, it's correct. There are no relevant deformations preserving the.
Right.
Yeah.
I guess we had other examples like, say, monster times monster, which is also self-dual under gauging rep H8, but it just doesn't have any relevant operator whatsoever. So yeah, we didn't find any symmetric arch flow.
Right. It's probably also hard to do it on the lattice. Because you might hope that some irrelevant deformation around the Ising square point can preserve this symmetry. And
right.
Coupling of the irrelevant deformation is very large. It might take you to some other interesting phases. But that you can hope to analyze very concretely on the lattice. But I think it's hard to realize this symmetry on the lattice. I don't know. I didn't really try. Okay, all right, thank you. I'm just curious if there's any such example of flows. Thanks.
Can I ask another question?
Yep.
Have you thought what is the symmetry TFT for this larger category that you get after you add this other duality line to the
Yeah, we are
rep
kind of
H8?
currently thinking on it's actually not that easy because the symmetry TFT of rep H8 is quite a large thing. So if you try to actually find a Z2 symmetry and try to gauge it, it's actually not so obvious. Yeah.
I think it could be easier if you start from, I mean, rep H8 is a particular Tambara-Yamagami category for Z2 times Z2. And in that case, you get the symmetry TFT starting from digraph width and Z2 times Z2, engaging a symmetry. Maybe it might be that it is just that instead of starting from the symmetry TFT for Tambara-Yamagami Z2 and Z2, you start from the symmetry TFT for digraph width, and you can identify a larger zero from symmetry that you can gauge. Maybe in that case, it's just invertible.
Yeah. I mean, I think Pashan also suggests this to me. I think the hard part is this Z2 symmetry would involve exchanging of the quantum symmetry you get from the gauging Z2 EM to get the symmetry of the Tambara-Yamagami. So that part is a little bit tricky.
So you're saying that the zero from symmetry that you get only emerges after you already gauged the zero from symmetry starting from Z2 times Z2. So it's not already present.
Seems to be that.
Okay, I see.
That seems to be the case.
I see. Okay.
Yeah.
Thank you.
I have a question which is related to the previous question. So when you have this rep H8 and you have an algebra and the theory is self-dual under it, and so you consider this self-duality line and add it to your fusion category and extend your fusion category. Is it a priori clear that is going to be a Z2 extension if you do that? And I think Z2 extension...
In general, no. In general, no. In this case, yes. In general, it could be like, if you just check a partition function, it's self-dual, without turning on any background field for the quantum symmetries, and then I think it could be a triality, it could be anything, right?
So is it that you're only looking for Z2 extension, or is it impossible to have Z3 in this case?
I think it's impossible because if you look at the symmetry of the same TFT, I think it's something like I think there's only Z2 subgroups there.
Okay, so you are saying that the symmetry TFT only have Z2 permuting symmetries of anyons, of their anyons. There is no Z3 symmetry which permutes the anyons.
Yeah, in fact, it was a Picard-Brunner group. It's like it's only contain order 2 elements. That's why you won't find these 3.
I see. And can you explain what are these other 2 data? So you have 3 plus and minus signs. I don't know if you are not. So one of them is the anomaly of this Z2 symmetry in the symmetry TFT, right?
That's right. Yeah.
What are the other 2 signs?
I think the other 2 should relate to the choice of the symmetries. That's the choice of Z2 symmetry. That's what we find from the interpreting of the boundary F symbol. So there's this map between the boundary data to the kind of the bulkish data, but we haven't worked out the details.
So the symmetry TFT have 4 Z2 permuting symmetries that permute.
Yeah, I'm not sure about this part actually. I'm actually kind of confused on this part. I feel like it should only have the Z2 permuting symmetry. The other 2 might just act triumphantly on the junction or something like that. Yeah, I don't have a good answer to this question at the moment. We're kind of currently thinking about it.
Okay. Thank you very much. Thank you very much.
Okay, if there are no other questions, let's thank Zhengdi again and let's stop the recording.